For this lesson, we're going to be reviewing the basics around functions. And this is something that's covered in the the MHF4U course, the grade 11 university math course in some detail, but it's something that we're going to be building on in this advanced functions course. And so you need to be either already familiar with this or you need to refresh that memory and go through this material in some depth to get it to the point where you're quite comfortable with it. Now, the very basics. First of all, before we start talking about functions, we have to talk about relations. And relations are any set of ordered pairs. Anytime we have a relationship between an x and a y or an independent variable, normally we call that x, but it doesn't have to be. And the dependent variable traditionally is y, but again, that doesn't have to be the case. And the way that we see that expressed most commonly is going to be when we do some sort of graph and we put our independent variable on the x-axis and the dependent variable on the y-axis. So that's why they typically end up getting named that way. Now, when we talk about this, we have an equation is normally how we actually first learn about sets. We actually represent our sets using an equation notation. So here we have a relation. This is saying that there is a relationship between y and x. Now, in this case, the way it's represented, there's no real reason to think that one of these or the other is the independent versus the dependent, other than the fact that we've got our convention here, which would make us think that the x is the independent variable, the y is the dependent. We've written this equation in the form y equals some combinations of x and some other constants, and that implies that y depends on the value of x. So that's an example of a relation. Here's another example of a relation using something that's a little bit newer, something we covered last year, which is set notation. And in this case, we have a set of points. So these are x and y coordinates. So that's an xy, that's an xy, and that's an xy. Each of these represents, another way we could think of that is that's point 1, that's point number 2, and that's point number 3. So that's another way to represent a relation. When we talk about relations, we are going to be spending a lot of time talking about identifying, manipulating these two ideas, domain and range. So domain is all possible values for the independent variable. In these two cases, the independent variables are the x's. So what values of x are possible? In part B here, that's pretty easy to see. The values of x that are possible are 0, 3, and 2. That's it. Those are the only possible values. In part A, it's not terribly difficult, but there's a little bit more thinking that goes into this. Sometimes when we're thinking about domain, we talk about what's allowed, but if you run into problems with that, if you can't look at something and say, well, what am I allowed to put in here? What I want you to do is think about asking yourself the question, what am I not allowed to put in here? Is there any value that I'm not allowed to put in? And in this case, well, this is just the equation of a straight line. Is there any x coordinate that I'm not allowed to put in here? Can you think of any value here that's going to cause some sort of mathematical problem? So that's the first thing you ask yourself. The most common mathematical problem that you're used to dealing with is dividing by 0. We're not allowed to divide by 0. Some students get tied up with that and they think about 0 being a prohibited value all on its own. There's nothing magical or special about 0 unless you're trying to divide by it. In this case, multiplying by 0, 3 times 0, there's absolutely nothing wrong with that. So 0 is not a restricted value. As it turns out, there are no restricted values here. So the set of all possible values, sometimes you can see what those possible values are. Sometimes you look for what are the impossible or the restricted values. Range comes from the domain after the domain has had its influence on the relation. Now, in the case, again, with part B here, the range is much easier. We just read it, 1, 4, -5. That's it. Those are the only values that correspond to the valid domain. In the case of the equation that we have here, not as easy to see, and that's why sometimes we will graph. That's why graphing is such a powerful mechanism in mathematics. But again, if I can put any number in here for x, what kind of numbers do I get for y? Or you can flip that over and say, okay, let me think about what kind of numbers might I not get for y? And both of those are valid approaches. We'll explore both of those concepts in more detail as this unit develops. Okay, so now that we've talked about relations in general, now let's talk about a function. Now a function is a very special kind of relation, and this is a very wordy thing. Students have a hard time with this conceptually. It's actually a very simple concept. I'm not saying that it's always simple to put this into practice. What it's saying is that every value of my independent variable only gives a single dependent variable, or a single answer. If I go back to that equation, y equals 3x plus 2, any number that I put in here for x, if this is a function, any number I put in here for x is only going to give one number for y. If this is not a function, then a number I put in here for x could give multiple answers for y. Now in this case, this is a straight line. It turns out this is a function, and we can just play this out very simply. If I put in 0 here, 3 times 0 is 0, plus 2 gives me an answer of 2. 0 is always going to give 2, and it's only going to give 2. There is no way that I can put in any number other than 0 to get a final answer of 2. That's the definition of a function. In set notation, it's even easier to see, and we saw that in our previous example here. Is this a function? We'll take a look at our x values. We have a 0, we have a 3, we have a 2. None of those x values repeats, which means for x equals 0, there's only one answer, y equals 1. For x equals 3, y equals 4. For x equals 2, y equals negative 5. Those are the only possible combinations. So when we look at set notation, we just take a look at the x values in our set, and we make sure that no x value is repeated. And when we're talking about graphs, and again, this is review, the idea of something known as a vertical line test. And we're going to take a look at that shortly. So the vertical line test is a very quick and easy visual way to determine whether or not a relation is actually a function by looking at the graph. When we look at equations, we rearrange for y, and we do this little these mental gymnastics to find out whether or not each value of x only produces a single value of y. Okay, so let's talk about set notation, because a lot of this domain and range is going to be involving sets. So we take a look at set notation first of all, and I've written it in words, and then I've written it mathematically, so you can see just how elegant it is. It contains a lot of information. It's very specific, but it really lets you express things a lot more easily than stating it, especially if you're doing it in writing. So what we have here is, first of all, the brace brackets, the curly brackets. That is the set of. So here we are defining a set. In this case, it is the set of all x. Typically, x would be the independent variable, so this could very well be our domain. So the domain of our function is equal to. In this case, though, I'm just talking about the set itself, so I'm not going to say that. Okay, so it's the set of all x. So here's where I define that x. Where x is a member of, that's what this very stylized E means. It's telling us member of, and then this stylized R is the set of real numbers. So this is x member of the real number set, which we normally reduce down to x is a member of R, or x is a member of the reals. Vertical line here, such that this is essentially now going to tell me what are the conditions under which x is defined. So it's not saying x is, if I just had this part just by itself, that would be saying x is a real number. Such that is saying that now there are some conditions that also have to apply. And in this case, fairly simple, x is any number less than 3 that also satisfies the type of number that it is, which in this case is a real number. So let's take a look at another couple of examples. So in this case, I've asked you to describe each set. This is a different one. Y is a member of this stylized capital Z. Well, in case you don't remember or that's not familiar to you, those are the integers. So this is saying that Y is a member of the integers. So that's already restricted what kind of numbers this can be. And then we say that -5 is less than or equal to Y is less than 3. And this is very important. Obviously, the difference between less than or equal to and less than is always important. But in this case, it ends up with kind of an awkward interpretation, and I put that in on purpose. So is -5 an integer? Yes. And -5 is less than or equal to Y. So in this case, it's saying that we can have -5. It's got to be between -5 and +3. So between there is -4, -3, -2, -1, 0, 1, 2, but then we get to this last one, 3. It says Y is less than 3. So although 3 would come next here, our value of Y has to be less than 3. So these are actually all of the numbers that define Y. Now this is a very odd way of doing this. You might even argue that it would have been easier to have done this as our solution set. Certainly would have been clearer. But what if this was -15 and this was less than 30? Would you want to write out all those integers? So there is still something to be said for a more generalized form. The difference that if I was putting this in here on purpose to make you think about this so we could talk about this, but if I was doing this, I would probably have put this as less than or equal to 2. So it would have been integers between -5 and +2 inclusive, meaning including the boundaries. But that's just one of the things that mathematics allows you to do. Now let's take a look at this next one, a little bit more complicated. I wanted to put this in specifically. Some of you may recognize this, although maybe not in this exact form, but this is something that we are actually going to run into in this course, so I'm kind of prepping you for it. So I'm defining in this case, I'm not worrying about whether this is domain and range, I'm just defining in this case, I've got Z. Now this one is a member of the reals, such that, but you can see in here I've actually included an equation. So I'm actually saying that Z is a real number, but Z is defined, so this is one of the conditions, where Z is defined as pi times k. So pi is the constant 3.1415, etc. K, well, I need to define K. I need to give some definition for that. And you can see I've included that here. You can typically use commas to separate multiple conditions. And here I say K is a member of, once again, this stylized Z, integers. K is a member of the integers. So let's think about that. Well, what's an integer value? 0, 1, 2, 3, 4, 5, -1, -2, -3. So in this case, let's start at 0. When K is equal to 0, so I'm going to list these. I'm just going to write this a little bit more room. I'm going to take my K values here and my Z values here. So let's put K equal to 0. If K is equal to 0, what is Z equal to? Well, pi times 0 is equal to 0. If K is equal to 1, what is Z equal to? Pi times 1 is pi. Not very nicely written. Pi. If K is equal to 2, pi times 2 is 2 pi, and so on. 3, 4, 5, ... What if K is equal to -1? Well, then this is pi times -1 is negative pi, and then -2 would be -2 pi, and ... This extends forever. And so if we were listing these, we would list them something like that. We would use commas to say it's this and this and this and this, and then the 3 dots indicates that the pattern continues, assuming I have shown you a sufficient pattern here that you'd be able to fill in the rest. Now this is about as simple as a pattern like this could get, but hopefully that gives you an idea. And this type of set notation where we define one variable in terms of another variable which we then also have to define. That's something that we're going to be seeing a little bit later in the course. Okay, let's talk about, here's a set, so it's a bunch of points. So I'm just going to assume my scale is a nice square scale. Put that as my x, my y. And I'm going to plot these points. 1, 2, 1, 3, 4, 5, 6, 1. And we ask the question, is this a function? Now there's a couple of ways we could look at this. Well, if we looked at it in terms of just the set itself before I graph it, I have 1 here with the value 2, I have 1 here with the value 3. So already, because of this, it's not a function. I can show that this is not a function in another way, which is something known as the vertical line test, which is the vertical line through, so this is the vertical line x equals 1, and as you can see, that vertical line x equals 1, it actually passes through 2 of these points. So this one fails the vertical line test. So it's in either case, no, it is not a function. And I've written that out in a slightly nicer form here. So if we take a look at it, so first of all, it's not it's not a function because the independent value, which are these x coordinates, we have a duplicate. When x is equal to 1, there are 2 possible values. When we plot it graphically, it fails the vertical line test. So we've got 2 independent ways there. Normally, if you're asked, you only have to come up with one way to show that something's not a function. And we can apply the vertical line test further. Here are some examples where we can try to make use of the vertical line test. Just take a quick look at those, go through those in your mind, and then I will go ahead and apply the vertical line test to each of them. So here we have this line. It's 2 distinct lines, but if I do a bunch of vertical lines, those vertical lines only ever pass through a single point. So this one is a function. Here we have a parabola. If I do vertical lines, normally you don't draw the lines in, you just imagine them being drawn in. But again, each of those vertical lines only touches 1 point on the parabola. Quite obviously, we get to here, we have a circle, and you can see, for example, here and here, here and here. And my vertical lines are not great here, but the vertical line test is pretty clear. This one is not a function. Here, vertical lines are only going to touch 1 point. It is a function. Here, vertical lines, and you only need to, and this is an interesting thing in mathematics, and it bears repeating, once you show one false case, that's all you need. You only need one to be false. So in this case, it has failed the vertical line test once. It is not a function. Here, we have vertical lines would only touch once. This one is a function. This is a function we're also going to be looking at in a little bit more detail in this course. Okay, what about an equation representation? Can I get any information out of this? So this is not a trivial equation, and we are going to, again, we're going to assume x is our independent variable, y is our dependent. So let's go ahead and put this into the form y equals. So the way I'll do that is I will cross multiply or multiply both sides by y. And then I will divide both sides by 1 plus x. Just rearranging at the same time. And now we ask ourselves, if I put values in here for x, is there any value that I can put in here for x that gives me multiple values for y, gives me different answers for y? And the answer to that is no. A little more interesting here might actually be to come up with the domain and subsequent range for this. I don't know that we're necessarily ready for that now, but just as a little mental exercise, let's take a look at the domain. So the domain is equal to, we're assuming it's x. We're going to look at real numbers. That's how I do that stylized R, 2 vertical lines and then I finish the R, such that, now what are we allowed to put in here? Or you might want to think, what are we not allowed to put in here? The only real restriction we have is on this denominator. I am not allowed to divide by 0. So the only restriction that I can see there is that x cannot be equal to -1. And that's how I would represent that domain. But the question was, is this a function? So, provided I don't put in x equals -1, is there any number I can put in here for x that will give more than one answer for y? And the answer to that is no. I can put in any number I want, and every time I put a number in here, I'm going to get a single answer for y. And I think the counterexample, which I've got here, is going to help to illustrate that. In some ways, this counterexample is almost painfully obvious once you do what I'm about to show you, which is we're going to rearrange this for y. Well, the first thing I need to do that is rearrange this for y squared. I end up with 9 minus x squared. And in order to get this as y, I have to take the square root of both sides. But when taking the square root, I have a variable involved here, so I always have to consider the positive and negative solutions. And you can see from that, right there, that positive and negative right? That means there are two possible answers. There's a positive answer and a negative answer. And if you remember, this is the equation, if you recognize it, this is the equation of a circle. And if we go back to our vertical line test, we already covered one of those. Here is a circle. It fails the vertical line test. Well, this one's going to fail for the exact same reason. And so if I put in a value here for x, now let's choose something that is simple. Let's put in x equals 0. So here I will set x equal to 0. Y is equal to plus or minus the square root of 9 minus 0, which is plus or minus the square root of 9 plus or minus 3. Two answers here. So a single value of x leads to two possible answers for y. Obviously, this is not a function. And I believe I'm wrapping up here with this one, the idea of function notation. So we are used to, and this is, I've been using this example already, which was written previously as y equals x plus 2. And that is a relationship between x and y. If we have a function, we are permitted to use this special notation, which is saying that we have a function called f, and it is dependent upon x. And it's kind of, again, a such that thing, but this function is defined, f of x such that, or defined by, is equal to 3x plus 2. So this is telling you when you input certain values of x, you're going to get certain values of the function f of x. The reason, or the tie-in, the way these things tie together, is that when we graph, and I showed you a graph previously, or I just a very rough sketch, typically x goes along that's the independent variable, is typically given the variable x, and then we normally graph the function along the y-axis. And so that's why the variable y and the function itself are generally viewed as interchangeable. Outside of this course is not something we're going to cover here, but if you carry on with some mathematics or mathematically intensive work in physics, engineering, that sort of thing, you may come across functions that are functions of multiple variables. And then the whole idea of x and y being independent and dependent, these are just conventions, and we make and break these conventions as they suit us. That's different than rules. There's no rule that says x is the independent variable. It just happens to be the case for much of the time. But here we would have, in this case, this is actually a function of 3 variables. Or if you don't like that, well, maybe you've got some other function which is a function of a, b, and k. Who knows? So you can have functions that have more than one input and an output. Now, I don't want to confuse the issue too much there. I was just kind of giving you an idea that function notation is used because it allows you to express things that become more difficult if you use this kind of limited notation that we start off with. We start off with this because it's simple, and simple is good. But there's a reason why we start to bring in complexity as well. Okay, that's it for this lesson. Remember, this is just a review. You need to, if this doesn't seem very familiar to you, you need to go back and review your own material where you covered functions, domain, range, set notation, vertical line test, all of those sorts of things. Those were covered in detail in your previous course, and those are things that you need to make sure that you're quite comfortable with before we get through this first unit.